So this is the third video, heading straight into analysis. Now, I'm talking about analysis. I'm going to write it up here. So this is the file that we're working on the last two videos. So we've gone down to data, and we're going to start analysis now. And we're still going to use the weight of kiwi birds data just for this practice and as an example. And you can, of course, as you're doing your data set, write similar things as we go on. Let's go heading analysis. Now, in analysis, we're going to have 3 to 4 parts. Those 3 to 4 parts are going to be the centers. We're going to talk about what they are. It's going to talk about the shape, the spread, and unusual features. Okay, as it is said in the slide. The slides for this starts off in the second slide, the same one with plan and data. It starts off there, the first part, the centers part starts off in this slide, and then you'll have to go to the next slide for shape. And we'll do that. But as we go in through it, we're going to talk about these 4 things in analysis. So they are sort of our subheadings under analysis. Now, just a note, in analysis, in almost every time, so when we're doing center, it's the same thing. When we're doing shape, spread, unusual features, it's the same thing. We normally have one sentence or one statement about group 1, whichever group that is. In our case, it's the female kiwi birds and male kiwi birds. For your one, it will be whatever it is, whatever group you are looking at and then comparing. So we're going to have one sentence about group 1, one sentence about group 2, comparison between the groups if possible. So for me, group 1 will be, if I'm talking about center, I'll tell you the center for the females. Another center would be, this is the center for the male. And then comparison would be, the center for the females is higher or lower than the male center by how much, right? And also a possible reason why this might be the case, right? So if it's very different, maybe why is it so different? If it's not very different, maybe why it's not very different. So have a think about not just comparing numbers themselves, but also going back to the thing that we are comparing. So right, so in this case, we're talking about kiwi birds. So going back to kiwi birds, I wonder why this is the case. So with this sort of template just sitting there, let's start centers. So in centers, mainly we are going to talk about medians, right? Medians, that's the one we're going to talk about. And the median is, if you lined up all your data points in a row, median is the one smack dab in the middle, right? So it's a little different to your mean, which is sort of your classic averages when you used to work them out, adding them all up and stuff. But median is the data point that is in the middle. Now, fortunately for us, we don't have to work out anything because NZ Grapher has done that for us. So having a look here, the top one is the female kiwi birds. So if you look here, that third one there that says med or MED, that's short for median. So 2.9015, that number there, that is the median. I know it has no units, but we know we're talking about weight in kilograms. So we know that is 2.9015 kilograms. That's the median for female. And we can do the same thing for males. So let's do one at a time. So I said, we're going to have one sentence about group 1. So I'm going to say the median of, not group 1, I'm going to say the median weight of you know what, okay, wait, sorry, of the sample of female kiwi birds. So the median weight of the sample of female kiwi birds. The sample is the data points we're looking at. We're not looking at every single female kiwi bird in the world. We're just looking at however many ones that we have measured or we have the data for. So that's why we call it the sample. It's not necessarily every single kiwi bird. Now, the median weight of the sample of female kiwi birds is, and then we just look back up there, 2.5 kilogram, not kilometers, kilograms. Cool. Same thing, the median weight of the sample of male kiwi birds. And I know your words can be slightly different. Maybe you have a different sentence. Maybe your sentence is less clunky than mine. But still, if it gets these points across in this way, that's fine. All right, male kiwi bird median weight, it's right there, 2.246. Is 2.246 kilograms. Right? And we have a calculator on us, so we say something like the female kiwi median is higher, or you can say heavier, than the male kiwi median by, and if you are comparing, they are two numbers, we can say one's bigger than the other. Tell me by how much. So you can just put this in a calculator. We do the bigger one minus the smaller one. Let's just work that out. Let's work that out. Let's try that out. So we say so it's the bigger one, right? This one is the bigger one. Minus 2.246. Boom. So there we have it. It's bigger by 0.6555 kilograms. Right? So there you go. That's the three sentences. Now, a possible reason why this might be the case. Let's have a look. Let's see why we think that might be the case and answer that question. Just go through in here. All right, so let's have a look. So I don't know. This might be because, and then we think of something, or maybe because there are more heavy females than males in this data set. Boom. Something like that, right? Let's carry on. Okay, and that's it. Centers is just the median, right? It's where the middle point is, and maybe that helps us to know if female kiwi birds generally tend to be heavier than males. So that's that middle line there in the box. That's that middle line right there and right there on the graph. Although, of course, we are reading there and there for the median. The exact median. Cool. Moving on to shape. Let's just bring it down there so it's on the new page. All right, coming into shape. Now, let's just flip over to the other slide. Cool, we got the analysis shape slide up. This is the week after. So the shape. The shape is the shape of the dot plot. So having a look at this dot plot, right? We're trying to gauge what kind of shape it falls under. And there's a couple of names for some shapes that you'll see. So we'll just need to know those terms and use them to describe the graph that we have. So here we go. This the most common one is called a normal distribution. That's the most common one. The normal distribution, I know the one in the example here on the slideshow here is very exact. It's a very perfect normal distribution curve. So it looks like a bell. It sort of has a big point in the middle where there's the most points there. There are the most points in the middle, sort of gathered around it. And then it sort of tapers off. It fades away either side. So that's the normal distribution, and that's the most common. Now I know our graph not necessarily exactly like that, and most data sets will not look that perfect. But if it falls in that sort of general area, we can say that it tends to be, the data tends toward a normal distribution. So if you saw this, you that's what you'd say. Let's look at some other shapes. Now, this is when the normal distribution, right? It is normal. It does have a central area where there's the most points. It's gathered up, and then it tapers off. But if it tapers off, like not in a symmetrical way, it definitely tapers off to one side a lot more, has a long tail on one side, we say it's skewed, right? We say it's skewed. So that's what we say. If the tail goes really long over to the left, we say it's left skewed, it's skewed to the left. If it has a really long tail to the right, we say it's skewed to the right. Okay, well, maybe I can do a quick drawing of that one. So if the shape looks something like that with a long tail, that's a skew to the right, right? It's got the long tail to the right. If your data does look like that, that is still kind of a Bell distribution, like a normal distribution, but still we say it's a skew to the left. Please excuse my bad handwriting right now. Yes, my writing surface is not flat on the ground right now. Flat on the table, I mean. Anyway, so shape. Talking about shape, we can say that, and then we look at our graph again, and do we say, is it really clearly skewed in any way? And we say no. In this one at least, the kiwi bird dot plot that we're seeing here, it's not skewed. I know you can say it's slightly longer this way, slightly longer that way, but we're really not looking at slight differences. We're looking at sort of clear, general, overall, sort of which ballpark it falls under, right? Okay, modality. We don't need to know the word modality, but we need to know the word bimodal and uniform. So bimodal just means if you have, they're saying peaks here, but it's where all the data points are bunched up. So if there are 2 points where they sort of peak, where the data points bunch up, we say it's bimodal, right? Now in our case here, still that sort of peaks around the same area. We're not talking about these little tiny little clumps here, like that one and that one and that one and like that one. That's not enough to say that it's bimodal or multimodal, anything like that. We still say that's just one general peak in the central area, right? So we're still happy with calling that a normal distribution, right? A bimodal is much clearer, right? It's like, it has that and then has like another bunch somewhere else, right? So we have to be happy with some amount of inconsistency with things like this. We're still happy with it. We're still happy that it generally looks like a normal graph. So that's the language we're sort of using. So let's have a look at that language and let's write our sentence. Well, the sentence for this example anyway, the kiwi bird weight example. So looking at shape, we say, again, we're looking at this bit again. We need to talk about both groups separately. In this case, it's not possible to compare. Like there's nothing to really compare it with. It's not a number bit that we're talking about. But anyway, let's start with it. So the data for female kiwi birds, right? We talk one at a time. Tends toward, the word tends toward is a really important one. You need to put that there. Tends toward A, and we look at it again just to double check. And yes, I'll say that's a normal distribution. A normal distribution, right? Is it skewed? It's not skewed, so I don't have to write about it. If it was skewed, I would say the data is left skewed or something like that, or the data is skewed to the left. But it's not skewed, so I'm just going to stop there. Yeah, actually, and that's about it. In this case, it's actually really quite simple. There's really not much more to talk about it. It's not bimodal. It has no skew. So that's all we really need to say. And we can say the same thing like this. The data for male kiwi birds tends toward a normal distribution, right? And I know that's not being particularly clever with our sentences, but that's fine. We are just reporting, right? This analysis is a report of our findings and of the data. It doesn't need to be a riveting read, right? So don't need to get too creative about it. So we don't need to worry about that. So a possible reason why this might be the case, why if it was bimodal, we'd say why it was bimodal. If it was skewed, we'd say why is it skewed? In this case, it's not skewed. It's a nice normal distribution. It's quite a clean normal distribution for the most part. Yeah. So in that case, it seems like this could be because we have a large enough sample size, right? So we've collected enough data to get a nice normal distribution, because that's how normal randomness would kind of work. If it was tending towards an average. So we have, this could be because we have a large enough sample size, and it represents the population, which is, when I say population here, when I say sample, I mean the data points that we have. The population means everybody, including the sample that we have, all the kiwi birds that we're trying to assume for. Represents. So it could be because we have a large enough sample size and it represents the population, right? So maybe we have a really good graph. Maybe we have a really good data set here, and it's quite, quite accurate. Okay. Now, usually when it is unusual, it's more, we have more to talk about. But since it is a very clean normal distribution, we are saying maybe the data is quite accurate. It's quite nice. It has plenty of data points, right? It's measured plenty of kiwi birds, that it has a graph, that is quite good for us to analyze. Okay, let's talk about spread, and let's go on to the next slide. Okay, so this is spread. The spread means how spread out are your data points, right? If I measured 100 Green Bay High School students for their height, if I asked 100 Green Bay High School students, I wouldn't just get one height. I would get, a variation of heights. And sure, it'll sort of center around somewhere that's an average. Like, it wouldn't be all bunched up in like 50 centimeters or anything like that. That wouldn't make any sense. But the spread means, okay, how varied? What is the diversity that we have here in our data? If it is very spread out, that means, the female kiwi birds, they tend to be, wildly varied in their weight. If the spread is tiny, that means most of these data points, most of these female kiwi birds in our sample, there's not much variation. They're pretty much the same, right? So some animals, you will notice that they are, very similar to each other, right? I remember when I was young being told that cheetahs at the moment, they are genetically really similar to each other. So all the remaining surviving cheetahs, they're really quite similar. So of course their diversity, their spread, if I had to measure things about them, the current cheetah population, it would be quite small. So that's the kind of stuff we want to work with. Of course, if the spread is really large, then it's harder to determine whether one group has a higher weight or higher length or whatever it is that we're comparing than the other. Okay, let's talk about spread. Let's talk about how to write spread, how to talk about spread here. We're going to talk about something called the interquartile range. Now, that's the one we need to talk about, right? Interquartile range, and that's it. Now, interquartile range is the range or the distance between that line in the box and that line in the box. It's the size of the box. And that box is where the middle 50% of the data points live, right? So that's 50% there, and the rest of that space is the rest of the 50%. So you can see that it's quite bunched up in this data set anyway. Okay, how to work out the interquartile range? Now, unfortunately, interquartile range is not actually here. We have to actually do a little bit of math for it. So I'll talk about how to get it real quick. Here we go. So group one, I want to talk about group one first. I want to explain the interquartile range, which is our spread, our measure of spread. It is, and you have it in the slide on the left there, it is, here's the UQ, here's the upper quartile. We call that the upper quartile, which is exactly where this is, where that point is. So it's like 3 point something, but it's less than 3.5. It's somewhere in there. And the lower quartile, which is exactly where this line falls, which will be 2.7 or 2.6 or whatever. Oh, it is. So there we have it. Those two numbers are the ones we need. And here's what we do. We have to do UQ minus LQ. So upper quartile minus lower quartile. This is every time, by the way, to find the interquartile range. So let's do that. So for the female kiwi birds, UQ is 3.192 minus the lower quartile, 622. Boom, it's 5.7. Okay, cool. I'm going to go here, go to spread. And of course, I'm going to need to talk about group A first. We can't say spread or the measure of spread, but since we're being specific, the interquartile range, which we can say is IQR from now on, for the sample of female kiwi birds is 0.5, 0.5, right? So, carrying on, you can add, yep, I'm just saying IQR now, for the sample of male kiwi birds, I'm gonna push that over there, is, and then we go back here, and let's work it out. So here's the LQ, here's the UQ. I need to go UQ minus LQ, right? Upper quartile minus the lower quartile. So 2.429 minus 2.069, boom, 0.36. So we say the interquartile range for the sample of male kiwi birds is 0.36. Yep, and don't forget, we are talking about kilograms, so let's not forget to put in kilograms. Okay, and we can compare, like, it's a number, right? Interquartile range, whatever that is, 0.57. It's how spread out that middle box is, and we care more about the middle box than the rest of the whiskers. It's how wide this box is, how spread out the data points are. And since that's a number, we can compare. We can say things like the IQR for the female kiwi birds is larger than the IQR for the male kiwi bird by, and I go 0.57, wait, I'll go here. I go 0.57, that's the bigger interquartile range, that's the female kiwi bird's IQR, minus the male kiwi bird IQR. It's bigger by 0.21. Oh, I keep saying kilometers. Yeah. Any reason why we think that, well, the female kiwi birds at the moment has more range, right? It has a larger range. It has more variety in their weights, apparently. So any reason why that might be the case? And sure, we're allowed to reuse things from our hypothesis and stuff like that. We're allowed to Google things and write in what we find out about our data. So I can Google stuff about kiwi birds and things like that. You can use information that you already know about the data set that even though it might not be in the data, you can use your general knowledge to think about these things. So, right, I mean, it could also be, this could be because, of random chance, right? It could be because of random chance or random sampling error, like it's just pure luck that we just happen to have measured female kiwi birds that are more varied in weight, while we've just by sheer luck or sheer chance we've measured more male kiwi birds that are sort of more similar in their weight range, right? Maybe that's the case. It could be. I'm not saying it is, I'm not saying it isn't, I'm just saying it could be. It could also be, and I think I said this before, this is one example that we used, it could also be because female kiwi birds carry eggs, or we should say can. They don't all carry eggs all the time. This means a kiwi bird with an egg would be heavier than the one without an egg, right? This could cause more variation, right? It just could be more, just a wider range of weights, right? When I say variation, that's that. Boom. That's spread done. Okay. Now, going over to unusual features. Unusual features. Boom. Yep, there are some videos there. Okay, going back to the last one. Oh, this slide goes over everything. Goodness. Should have used this one from the get-go. I just wanted to go step by step as they were uploaded, which is why I did what I did. But anyway, unusual features. It just means a point, like it could be a single point or it could be a bunch of points that's just kind of very far off, like very clearly off the norm, like it's just not in the group. So if it's more than one, we call it a cluster, right? If it's a bunch that's in the wrong, in a really odd place, that's called a cluster, an unusual cluster. If it's just one, we say it's an unusual point. So we look at our graph, we look at our dot plot, and you're sure that's this dot here, that's quite far off, but really it's not that bad, is it? Having a look at this here, it's not that bad. It's not extremely far off, like unusually high. It needs to be quite clearly weird, like it's due for some explanation. Like it doesn't make any sense. So this, I reckon, still falls under a normal distribution-ish kind of curve. It's not stupendously odd to have this point here. So I think that's all right. And of course, this one here, yeah, there's really not much. I mean, it needs to be like a point here or something, right? That's really quite high. But since there are no unusual features, there's really nothing to write, right? So if there's nothing to write, I would not write it. I would simply put it all away. And I would just end my analysis there. That would be the end of my analysis. And that would be perfect. That'd be great. You don't have to write unusual features. That doesn't mean more marks or anything like that. It just means if there were unusual features, you'll talk about it, and that's correct. If there aren't unusual features, you don't talk about it, and that's correct. But since we are just doing an example here, if I were to write an imaginary unusual feature, right? Like, I don't know, maybe I had, maybe this dot here, right? Maybe it was really quite low. Like, maybe it was like way here or something, like way here or something. Like, 0.2 kilograms or something immensely small, like way too small to be just forgotten about. Then I would say, there is an unusual point, or you could say a cluster, depends on what you have, but you say there's an unusual point in the, and then you say which group, right? It could in the male sample, or you could say female sample, but you know, in our imagination, in our imaginary scenario here, we're saying there's a really low unusual point in the female sample. So I would write it like this: there's an unusual point in the female sample. The weight is well, the weight is very low. You can say the weight is very low for the majority of the group, right? It's unusually low. And then we talk about why it might be the case. And of course, unusual features, we don't need to do both groups. We just need to talk about the ones that we have. We don't need to compare because they're not necessarily related. We just need to explain this, the one that we have, and a possible explanation for why that's the case, right? So if it was a really low weight in the female category, I could say it could be a very young kiwi. Accidentally added to the sample. Maybe, you know, maybe it isn't, right? Maybe I'm getting it totally wrong, but I'm thinking about possibilities that explains it. It could be an entry error. An entry error is when somebody was writing the weights down, they just made a typo. Like maybe it was supposed to be 2.2 kilograms, but they wrote 0.2 kilograms, right? Like that's just a typo, right? 2.2, but they just wrote 0.2, and the computer read it as 0.2 kilograms. So that would be like a typo. That was just an entry error. Oops, daisy, phone call's coming. One moment. Okay, took the call. A bunch of things happened since, and now I'm back. So please excuse if I have any continuation errors. What am I saying? Okay, sorry if it doesn't make sense, but I'll try to make it as fluid as possible. Anyway, but the thing is, I think I'm actually done, haven't I? I finished unusual features. So if there is an unusual feature, like an unusual point or an unusual cluster, mention it. Make some assumptions about why that might be the case, and that's actually it. We've actually finished analysis. Right, so this is the general rule we're going by. Like when I say one sentence, it doesn't necessarily mean one sentence. It just means mention the thing about group 1 separately, mention the thing about group 2, possibly compare if it's a number thing, and if there's any reason in the population that this might be the reason for, or maybe in the sample, yeah, a possible reason why this might be the case. So this is actually, of course, not something you would actually write down in your assessment. This is just the guide that I've written down, so I'm just gonna take that away, put that here. Yeah, and there we go. That would give me centers, shape, spread, unusual features, and done. Right, that's all inside analysis. Now we only have one more part to do, and that'll be the next video. So hopefully that'll be shorter than this one. This is the longest one. This is the most, yeah, analysis is definitely the longest part of this assessment. All right, otherwise, take care, everybody.